Usually we look at prime numbers as unpredictable points scattered along a flat, one-dimensional number line. To find the logic behind their distribution, we look past the numbers themselves. Instead, we isolate the empty spaces between them, the prime gaps. This diagram shows how we map those distances onto a two-dimensional space. We need two rules: a radius, defined as the reciprocal of the prime gap, and an angle, determined by the golden ratio. These two formulas take that sequence of distances and convert them into geometric coordinates, creating a space where we can begin to evaluate the distribution as a physical shape. Test prime 5 on our polar grid. The gap from the previous prime, 3, is 2. The radius is the reciprocal, 0.5. A gap of 4, like between 13 and 17, yields a 0.25 radius, pulling the point closer inward. This mapping creates an inward growth. Instead of a number line stretching off into infinity, massive gaps are physically compressed into a tight central core. Now for the angle. Multiply a full circle by our prime, 5, divided by the golden ratio. Modulo 2 pi means the arm spins fully around, recording only where it stops. This irrationality acts as a dispersant, preventing predictable spokes. By anchoring the rotation to the golden ratio, we guarantee every single prime will find a unique, non-overlapping home on the plane. How does this apply to prime 7? What is the gap, the radius, and the angle equation? Take a second to map it out. Prime 7 follows 5. The gap is 2. It shares the 0.5 radius rotated to a golden angle. Accelerating, we plot 11, 13, 17, and 19. Notice 11. A gap of 4 cuts its radius to 0.25, yanking it inward. This repetitive process proves that the unpredictable jumps between prime numbers can be resolved into a stable geometric structure. This maps the first 1,000 primes, resolving individual points into a global structure. The outer boundary dots represent the smallest gaps. Frequent clusters push toward the edge. The dense core represents prime deserts, as reciprocal math mechanically pulls those large gaps toward the origin. Mapping this hidden rhythm requires 3 steps: finding the gap, calculating the reciprocal radius, and spinning the point by the golden angle. Mapping prime gaps through complex geometry demonstrates that the sequence is governed by stable statistical laws. This transformation reveals the rigid, structural order inherent to the distribution of prime numbers.